So in the last class, we had seen, we had started with this chapter, chapter number 30. I hope you can hear me. And what are the things we have seen there? The first thing we have seen is what is a capacitor. Then the second thing we saw was the relationship between capacitor, potential difference, and the charge. And we have seen that the capacitance value does not depend on the charge and the potential difference. It's a constant for a given combination of two conductors. Then the third thing we have seen was the relationship between electric field and potential difference. We set up an equation. We have seen that delta V is going to be equal to integral of minus E dot dr or dl. Okay, using this, we found out the expression for capacitors, capacitance formulae for parallel plate capacitor. Then we saw the expression for a spherical capacitor, and finally for a cylindrical capacitor. Okay, so this is to summarize what we have done in the previous class. Okay, now today let's just go ahead and continue. So what is it we are going to see in today's class? We are going to see that, as I mentioned in a previous class, capacitors are simply circuit elements, and you're going to see capacitors everywhere in any kind of circuit you take. Maybe even a microcircuit or even in your VLSI design, everywhere there are capacitors. But only thing is, in those kind of situations, the capacitors you have would be extremely small. Okay, and in a lab, typically you may require for certain fabrication purposes, you may require capacitors of certain values. Let's say you want a 50 microcoulomb capacitor, but then a manufacturer may not be making this 50 microcoulomb. They come out with certain values of capacitors. So what do you have to do there? You will have to put together a certain number of capacitors in parallel or series or combinations of parallel and series in such a way that you are able to get the capacitance value that you want. Okay, so basically today what we are going to see is how do you combine capacitors in series and parallel. Now before we do that, we need to understand one term that's called the equivalent capacitance. What is the meaning of equivalent capacitance? If I'm going to take capacitors, put them in series or parallel or combine them, okay, then that combination, let's say I'm talking about a combination like this. Okay, let's say this is C1, C2, C3. I combine it and I have the rest of the circuit. I'll call these two terminals as A and B. Now, equivalent capacitance means I should be able to substitute these three with one single capacitance of value some C equivalent. Okay, and the rest of the circuit should behave in exactly the same fashion. The rest of the circuit means I may be talking about the current, I may be talking about the voltage. Okay, the rest of the circuit, okay, should behave in exactly the same fashion, or there should be no change in the operation of the rest of the circuit, or the rest of the circuit should not be able to realize that you have substituted three capacitors here with a single capacitor. Now this kind of a substitution of one single capacitor in place of a combination of more than one capacitors is called the equivalent capacitance. So today we are going to try to find out what would be the expression for equivalent capacitance. Any doubts? No doubts? Okay, anyway, you're all very intelligent, you don't have any doubts. So, going ahead, let us see that there are two types of combinations. One would be the series combination of capacitors, and the other would be the parallel combination of capacitors. Let's see what each of them would be. Please remember, in your school days, you people have been studying resistances. Even today, when did I finish my school days? Even today, I tend to think of only capacitors in parallel. I tend to confuse with capacitors, resistors in parallel and capacitors in parallel. Please don't make that mistake because students tend to make this mistake. So first, let us start off with capacitors in parallel. Now, what is the meaning of connecting capacitors in parallel? So look at this. You have a figure here. You have two capacitors C1 and C2 connected in parallel, and you have two terminals A and B here. Okay, I'm talking about this figure. And what is the equivalent circuit? The equivalent circuit will be combination of the C1 and C2 into one single capacitor with capacitance value C equivalent. Okay. Now, what is the meaning of combining in parallel? Combining in parallel means just there are three things to remember. 1, 2, 3. The first thing is in traveling from terminal A to B, there are more than one ways of traveling from A to B. There are more than one way of traveling from A to B. And along any of these paths, you will encounter only one capacitor. Along any of these paths, you're going to encounter only one capacitor. Now, because you have two capacitance, you can say that there are two paths taking you from A to B. And whichever path you're going to take, you're going to come across only one capacitor. Okay, that's the first criteria. The next thing is the same potential difference delta V would appear across each capacitor when a battery of potential difference delta V is connected. I told you the other day, what would be the potential difference that you can create? That would be equal to the potential difference that your battery is able to provide. So let's say that you're going to connect this A and B to a battery which is able to give you a potential difference delta V, Then connecting in parallel means the potential difference between these 2 points will be delta V. Similarly, the potential difference between these 2 points also will be delta V. That is, the same potential difference will appear across each capacitor. That is also one thing that you should see when you're connecting capacitors in parallel. Now, let's come to the third point. What is the third point? The third point that you should remember is that charges are conserved. So the total charge, let's say there is a charge I flowing, a Q flowing through this. Okay, the total charge flowing per second is current after all. So the total charges flowing here, okay, will just get branched here and get divided between these two capacitors. Or the total charge Q is delivered by the battery. What is the job of the battery? Battery's charging means what? It is going to remove positive charge, electrons from one plate and leave it on the other, which is creating a potential difference. Okay, so the total charge delivered by the battery is shared between the two capacitors. That means if I have a total charge Q, which is going to be lifted by the battery from one end, then that Q will be deposited on these two plates in such a way that Q1 plus Q2 will be equal to Q. Okay? So that's one thing you have to remember. So if I say that this side is going to be plus, then this plate is going to have minus Q. That's also something that you should remember. Okay, now let's arrive at the relationship between C equivalent, C1 and C2. So what we'll do is consider the conservation of charges. So conservation of charges tells us that the net charge is going to be Q1 plus Q2. And you know the relationship between Q and delta V. You know that Q is equal to C into delta V. So for the first capacitor, if you write, you can write Q1 is equal to C1 into delta V. Similarly, Q2 equal to C2 into delta V. We have seen that delta V is common. Therefore, you would write it as C1 plus C2 into delta V. C1 plus C2 into delta V. Now let us come to the left side of the equation. Left side of the equation, we told you that when you put the equivalent capacitor, the rest of the circuit should behave in the same way. So that means here also the charge that you're going to get is going to be Q. So on this plate, let us say there is a plus Q. On this, there is a minus Q. And the potential difference is delta V. So write an equation connecting delta V, C equivalent and Q. So what would you get here? On the left hand side, you will write Q is equal to C equivalent into delta V. And you can see that delta V would just get cancelled out. Or you get C equivalent is equal to C1 plus C2. Again, remember, I've been telling you from the beginning that capacitance value cannot be negative. It's always positive. So when you connect n number of capacitors of capacitance value C1, C2, C3 up to Cn, then the capacitance of the equivalent capacitor will be simply the sum of all these capacitance values. Any doubts?
No, ma'am.
Okay. So now, the next question. I already gave you one reason why we have to connect capacitors in parallel series or combinations of parallel and series. I said if you want a certain circuit that you're going to make demands a certain value of capacitors, you can actually get those kind of values of capacitors by appropriately connecting capacitors. That's one reason. Then any other reason why you specifically connect capacitors in parallel? That's the next question. You can notice here that because C equivalent is going to be the sum of all the capacitors value, you can notice here that if I talk about any one capacitor, Ci, let it be the ith capacitor. I can be 1, 2, 3 till n. You will see that C equivalent is always going to be greater than Ci. Yes or no? The capacitance, the equivalent capacitance will certainly be greater than any of the individual capacitor values. Okay, therefore, by connecting capacitors in parallel, what you're going to do is, this would be a convenient way to increase the capacitance. It's a convenient way to increase capacitance. And another thing you can do is, by connecting the same battery, you're actually able to increase the amount of charge that you can store using that battery. If you use the same battery, which is going to give you a delta V potential, and then use one battery at a time. Okay, the first battery, the first capacitor will store only Q1, the second Q2, the third Q3. But then here you've seen that because the potential difference across the combination parallel will be the same, you can actually effectively store more charge by combining capacitors in parallel. So if you want to charge capacitors, just put them in parallel and then charge them. You will be able to effectively store more charges. And then you will ask, what is the need to store more charge? The answer to that question we will answer in a few minutes. Why our aim is always to store more charge? The answer you will get it in a few minutes. Any doubts? Okay, so now let's go to connection of capacitors in series. So here is a picture. You have capacitors connected in series. You have a capacitor C1 connected to a capacitor C2. Or if I have to draw the equivalent, I'll show it like this. C equivalent, terminal A, terminal B. Okay. So what are the characteristics of here? This is the problem with cutting and pasting. One sec. Series combination. Yeah. So three properties that characterize series combinations. Let us see. The first one is, in traveling from a point A to B, you have only one path. You have only one path that takes you from point A to B. And that path is going to include all the capacitors which you have connected. It's going to include all the capacitors that you have connected. Then you say that your capacitors are connected in series. The next important thing is, let's say that you have connected a battery which is able to give you a potential difference of delta V. It's going to give you a potential difference of delta V. Then what happens is, here voltages are shared. Voltages are shared. In parallel combination, what was shared? Anyone?
Charge.
Charge was shared. Whereas here, voltages get shared. Okay, so how do they share voltage? The potential difference between these two plates will be delta 1, these two plates will be delta V2, and you will get delta V equal to delta V1 plus delta V2. So that's another thing. Then what is the third point? The third point is that, again, this comes from conservation of charges, and then your charges are able to go only through one path. There is only one path which is through which the charges can travel. Okay, therefore what happens is, if Q is the charge that's going to be delivered, which is going to be carried, then what happens is, if I say that there is a minus Q, maybe I'll just change the polarity. Okay, so if I say that there is a there is a minus Q here, then this plate will have a plus Q, and similarly this will have a minus Q, this plate will have plus Q. Like this, if I talk of n number of capacitors also, it will be the same, or the charge on the plates does not depend on the capacitance value. Charge on the plates will not depend on the capacitance value, whereas in the previous case, you had Q1, Q2 that depended on the capacitance value. Okay, and another very interesting thing is, since you are finding plus Q and correct, yeah. So there is a plus Q, there is a minus Q here. There's a minus Q, there's a plus Q here. Okay, and okay, so this entire plate is going to be at the same. This entire plate is going to be neutral. This entire plate from here to here, this entire thing is a conductor, because after all, this connecting wire is also a conductor. This is a conductor, this is a conductor. Okay, so there is going to be this entire body is going to be neutral. This entire body is going to be neutral. Now the next question is, I thought somebody will ask me that question. Is there anything that you are able to think of when I have put this figure? Anything? The question that you should be thinking is, this it's a neutral body, madam, that's fine. There's a plus Q and a minus Q separated. Why should they be separated? It's the same body. Why are they not coming together? Positive charges and negative charges should be attracting each other. That should be a question. Nobody's asked that question. Try to answer that question. Now, since you didn't ask me that question, I am asking you that question. Find an answer to this. Did you understand my question? You have this H kind of piece you're having, no? This piece. This H kind of a structure you're having. This entire thing is neutral, I said. Why is it that this plus Q and minus Q are not recombining and, coming together? Because after all, there is a path, and after all, there is a conductor, and then positive and negative charge should be attracting each other. Why is that not happening? Try to answer that question. Okay? Now, come back. So we have seen that voltages are shared. So now what we'll do is, so here also you're going to have delta V. Okay, so this plate is going to have minus Q. This plate is going to have plus Q. Therefore, you can simply say that Q is equal to C equivalent into delta V. Or you can say that delta V equal to Q by C equivalent. So that's how you're going to get this side. Similarly, you can write delta V1. Delta V1 is Q by C1. Delta V2 is Q by C2. Or Q becomes common, take it out and then cancel it out. So you get 1 by C equivalent is equal to 1 by C1 plus 1 by C2. Or I can say that C equivalent is going to be, what would it be? C1, C2 divided by C1 plus C2. So this is the formula if it is just two capacitors. I can extend the same for any number of capacitors. I can extend the same for any number of capacitors. And then the next question is, why should we connect capacitors in parallel? Why do you connect capacitors in parallel? Would be the next question. You can see here that C equivalent will always be less than any individual capacitor that you have put in this combination. C equivalent will definitely be less than any of the capacitor that you have put in that series combination. So that means the capacitance value is going to come down. Yet, why are you doing this? Is the next question. Okay. You are not going to find this answer in your book. You're not going to find this answer in your book. Okay. The answer that is to this question is, you connect capacitors in series because this would be a convenient way to increase the voltage rating. This is a convenient way to increase the voltage rating. Let's see what it means. Do you remember in the last chapter we have seen something called dielectric breakdown? Anyone remembers what is dielectric breakdown? Anyone? We have seen that See, actually, between the two plates of the capacitor, right now we are having air or vacuum. That is also a dielectric, you must remember. Okay, but this vacuum or air can also become a conductor if you apply a large potential difference. When you apply a large potential difference divided by the distance between the two plates is equal to the electric field. So for any given dielectric, there is a critical value of electric field, which if you cross, the dielectric becomes a conductor. It will break down. And imagine two conducting plates with the material in between as a dielectric. So these two will not, the two plates will not be electrically touching each other. They are not electrically conducting. They are not able to carry charges from one plate to the other. But then what happens once there is a breakdown in the dielectric? What happens is you have a plus Q, there is a minus Q, very conducive. They just come together and the capacitor gets spoiled. The capacitor breaks down. Okay, so what happens is whenever you have a capacitor given to you, the capacitor has a certain rating. That rating tells you what is the maximum voltage that it can apply, that you can apply to it. You should not exceed it. Okay, so let's say you have a battery in your laboratory. That battery is able to, let us say, give 10 volts. But your capacitor has a rating of, let us say, only 4 volts. Your capacitor has a rating of only 4 volts, but your battery has 10 volts. Then how will you charge the capacitor? Anyone? If you directly connect it, the capacitor is burnt. So what will you do? Did you get my question? Anyone? I have a battery. Battery can give 10 volts, but my capacitor can withstand only 4 volts. That's the rating. Then what do I do? What do I do? Anyone? Did you even understand my question? Anyone has understood the question? Boss, I have a battery. That battery can give 10 volts. Okay. I want to charge my capacitor. My capacitor can take only 4 volts. If I exceed 4 volts, the capacitor will burn. It will break down. So what can I do? But I want to charge it. So what do I do? Nitin Chaudhary thought it's better to leave than to even think. Anyone? Well, if nobody is interested in thinking, what can I do? Akshara, looks like you're having an answer.
We can connect capacitors in series so that the capacitance would decrease and the voltage would be increasing.
The capacitance of the capacitance of the individual capacitor will not increase. That will remain the same only. But then the voltage gets shared. The source voltage gets shared. Therefore, your capacitor will not burn out. That's the right answer. Okay. So that's also one thing that you can achieve by connecting capacitors in parallel. So you should have these kind of questions. This question is definitely not answered in your book. Okay. So now let's quickly see whether we can work out a problem. Yeah. So what kind of a picture are you seeing here? C1 and C2 are connected in parallel, and the combination is connected in series. So you have to find out what is the equivalent capacitance between A, B. Let's say A, B. A, B. Okay. So first, what we do is you combine these two and call it as C12. So what will be C12? What will be the formula? C12 will be equal to. This is parallel. C1 and C2 are in parallel. Therefore, C12 will be equal to C1 plus C2. So what is C1 value? C1 value is 12 microfarads and C2 is given as 5.3. Therefore, the sum is going to be 17.3 microfarad will be the capacitance of this portion. or I won't write it here. Let me write it here. So this is 17.3 microfarad. Now the 17.3 microfarad is in series with 4.5 microfarad. C3 equal to 4.5 microfarad. Now I want the combination of these two. So how do I get it? Let me call that combination as C123. So this is a series. So 1 by C123 will be equal to 1 by C12 plus 1 by C13. Okay. So you can just do it and find out what is going to be the equivalent capacitance. Okay. And you should get C123 as 3.57 microfarad. Not difficult at all. All you have to do is just put 1 by C12, you put it as 17.3 plus, sorry, I made a mistake here by writing. It is not C13, it is just C3. C3 is given as 4.5. So you can do this and get your C123. So this is your answer. Okay, the problem doesn't end here. So what does it say? If a potential difference delta V between A and B, if you put a battery of potential difference delta V equal to 12.5 volts, okay, what would be the charge on C1? Let the charge on C1 be Q1. So what is Q1? Can you find out charge on Q1? So how will we go around doing this problem? Remember, this terminal is AB. So this terminal is AB. This equivalent is also AB. And what is the potential difference? Potential difference is delta V equal to 12.5 volts. So if I call the charge on this equivalent capacitor as Q123 and this is minus Q123, can I find Q123? What will be Q123? It will be C123 into delta V. C123 we have just done in the previous page. It was 3.57 microfarad and delta V you get is 12.5. Or you are able to get this charge on the equivalent capacitor as Q123 equal to 44.6 microcoulomb. Okay. So that means I know that there is a charge of 44.6 microcoulomb. Now let the charge on these plates be Q2 minus Q2 plus Q3 minus Q3. I'm sorry, I won't say Q2, it's Q12 minus Q12, Q3 minus Q3. Okay, what can you say about Q12? What will be Q12? What did we say when we were talking of parallel of combination in series? Voltage gets divided, charge will be the same we have seen. So therefore you can say that Q12 will be equal to Q3 will be equal to Q123, which is equal to 44.6 microcoulomb. Okay. Now if that is the case, how do I get my Q1 next? What I should now do is I should find out what is the potential difference delta V1 between these 2 points. What is delta V1? If I say delta V3 is the potential here, I won't say V1, I'll say V12. Delta V12 and this is delta V3. Can I get my delta V12? Can I get this delta V12 if I know Q12? or this becomes 44.6 micro divided by C12. C12 I had already done, that was 17.3. Micro cancels out. So I get 2.58 volts. Okay, so delta V12 is 2.58 volts. Okay, now this just means that between this point and this point, the potential is delta V12. Between this and this, it is delta V. Now, can I find out Q1? Anyone? When I am connecting in parallel, I have seen that it is a charge that is shared, not the potential. So the charge on this is Q2, the charge on this is Q1. So I can simply say that the potential difference is the same, or I can say that Q1 is going to be equal to C1 into delta V12. I know what is my C1. C1 I already have, it's given in my problem as 12 microfarad. And just now I found out delta V12, which is 2.58. So I get my Q1 as 31 microcoulomb. Okay. Now, can you find out Q2? Can you find out Q2? The problem is over. What the author has asked, I have finished. Can you find out Q2? How many of you want me to explain this problem again? Is there anyone?
Yes, ma'am.
Okay. Why don't you ask? Just ask. No, I'm here to tell you. Okay, so what is given in the problem? You have three capacitors, C1, C2 connected in parallel, and this combination connected in series to C3 between terminals A and B. C1, C2, C3 values are given to you. Find the equivalent capacitance of the combination, of this combination. So that means I should be able to put one single C123 between A and B, and that should do the job of C1, C2 and C3. So how do I do that? First step, what I will do is I will combine C1 and C2. I'll combine C1 and C2 and call it as C12. This step is clear?
Yes, ma'am.
Right, I'll call it as C12. And then that is in series with C3. Right. Now what will be C12? C12, according to my knowledge of combination in parallel, is C12 equal to C1 plus C2. So I just have to add these two and I am going to get 17.3 microfarad in series with your 4.5 microfarad. This picture is clear?
Yes, ma'am.
Right. Next, I want to put these two fellows together and get C123. And you know they are in series. So what do? I use the formula 1 by C equivalent is equal to 1 by C1 plus 1 by C2. Just that formula you use. So therefore I will call the equivalent as 1 by C123. And then the first one is C12, no? So I write 1 by C12. The second one is C3. I call it as 1 by C3. Substitute the values. I get C123. Clear?
Yes, ma'am.
Right. Next, what we do is, there is a second part of the question. What is the second part of the question? The second part of the question says that if this original combination is connected to a battery, which is able to give a potential difference 12.5 volts, which is able to give a potential difference of 12.5 volts, what will be the charge on C1? What will be the charge on C1? There is no way I can directly get it. So first what I will do is, I will simply say Q1 is the charge on C1, Q2 is the charge on C2, Q3 is the charge on C3, let me say. Okay. And next what I'm going to do is, I will look at the next circuit where I have combined C1 and C2, and let me say that For this equivalent C12, let the charge on the two plates be Q12 and minus Q12. This, of course, is Q3. This step is clear?
Yes, ma'am.
Right. And I know that. So these two, you see this picture, what do I have here? I have two capacitors connected in series. And when I know that capacitors are connected in series, voltage gets divided. Voltage is getting divided. So what is the original voltage? The original voltage is delta V. Delta V gets divided into two parts. Let the voltage across C3 be delta V3 and let the voltage across C12 be delta V12. Is this step clear?
Yes, ma'am.
Right. And finally, let me go to this final picture. In the final picture, everything has been substituted with this one single capacitor. Let the charge on this capacitor be Q123. I'm saying Q123 because it's a combination of 1, 2, and 3 and has a capacitance value C123. And what is the potential difference it is going to see? It is going to see the entire potential difference because it is behaving like one single capacitor. So that potential difference is 12.5 volts. This is clear?
Yes, ma'am.
Right. Now, we have to start our problem from here. First step, let us find out what is Q123. You know Q is equal to C into delta V. So just use that formula and get your charge. So this charge is going to be 44.6 microcoulomb. Okay, once you're done with that, let us go to the next picture. This picture. When you go to this picture, you're seeing that here are two capacitors connected in series. In series means what did we see? Voltages will get divided, but the charge will be the same. There's only one path for the charge to flow. So you can say that Q12 and Q3 will be equal to Q123. This step is clear?
Yes, ma'am.
Right. So you straight away got your Q12, which is 44.6 microcoulomb. Okay. Next, I want to now find out what is this delta V12. So once more, use this formula. Q is equal to delta V into C. Just use that formula here. And you're going to get delta V12, which is 2.58 volts. 2.58 volts. Now go to the first picture. I know that this potential difference here is delta V1 equal to 2.58 volts. Okay. Therefore, now what I'm going to do is I'm going to look at individually Q1 and Q2. Instead of looking at it as C12, I'm going to look at them as Q1 and Q2 or C1 and C2 in parallel. And I know that this delta V12 is the same for both these fellows, for both these capacitors. So now I'm going to just take Q1 equal to C1 into delta V12. Okay, I know V12, I know C1, I can get my Q. Clear?
Yes, ma'am.
Right. Now, if you have understood all this, without any difficulty, you should be able to get Q2 also. What will be Q2? Q2 will be again C2 into delta V12. You can get your Q2. Similarly, if you want your Q3, what should you do? If you want your Q3, what should you do? Anyone? Not even one person who can answer this question. If I want Q3, what I should do? If I want this Q3, I should know what is going to be this potential difference. This potential difference is delta V3. I know delta V12 plus delta V3 equal to delta V. So I know delta V12, so get delta V3. Then from delta V3, get Q3. Okay. People who are interested in learning the subject, you can just take this one single problem, find out Q1, Q2, Q3, delta V1, delta V2, delta V3. If you can find these 6 parameters for this problem, that means you understood the concept very, very clearly. Kiranmai, will you try that?
Yes, ma'am.
Okay. Find out Q1, Q2. Just don't stop with what the author is saying. Find out Q1, Q2, Q3, delta V1, delta V2, delta V3. If you are able to do all these 6, that means you understood this problem completely. Okay? Okay. Now, let me just, another 10 minutes I have, let me just quickly see. I have mentioned one word, I don't know whether you remember. By connecting capacitors in parallel, I can put more charges on the plates. Do you remember my saying that sentence? I can put more charges on the plates. I used a sentence there. So what is that? Let us see. How does it help me? Let us see. You're seeing that you can actually, by charging a capacitor, you can actually store energy in a capacitor. I will explain why it is so. I have two plates. Initially, both of them have zero charge, zero charge. I have kept them like this. The wire is here. Okay. Now I'm going to connect a battery here. When I connect a battery, what is this battery going to do? I said there will be a current flow like this. That means there is a electron flow in the opposite direction. It will pull out electron from the left plate and put it on the right plate. Within a short time, this plate will become negatively charged. This plate will become positively charged. Is this clear?
Yes, ma'am.
Yeah. So, who is doing this work? Which agent is doing this work of pulling out electrons? It needs to do work. Simply, you can't just take out electron from a conductor. So, somebody is doing work. What is doing work there?
Battery.
The battery is doing work. The battery is doing electrostatic work. It is pulling out charge from one plate and putting it on the other. And therefore, what is happening is the negative plate is slowly become negative potential. The positive plate is slowly becoming positive potential, or there is a potential difference being built up. So the battery is doing work. In mechanics, do you remember one definition of work done? Work done is a way of putting energy into a system. Do you remember this? Like, for example, I have a block sitting on a table. It is at rest. Okay. Now, if an external agent comes from here and applies a force and pushes it, what is this external agent doing? It is doing positive work, force and displacement in the same direction. And what is going to happen to the block now when you're pushing it like this? What happens to the block when you push it?
Starts moving.
Starts moving. That means it's just got kinetic energy now. So work is a way of putting energy into a system. Okay. So here also what is happening is battery is doing positive work. It is actually pulling out electron and putting it on the other. Even otherwise, you people must remember an equation that you have all studied in your previous chapter that says that work done by electrostatic force is equal to Q into delta V. Do you remember this equation? Yes or no? You don't seem to remember anything. Okay. So what happens here is the battery is doing positive work of pulling out charge from one and putting it on the other. And there is a potential difference between the two. Potential difference is related to potential energy. Yes or no? Potential difference and potential energy are related. Yes or no? You remember this?
Yes, ma'am.
Right. Actually, you have to put a minus here. So work done means you're actually creating a potential difference, or in other words, you are putting energy into the system. You're putting a potential energy into a system. And how are you doing that? You're doing that by pulling out an electron from one plate and putting it on the other. By separating charges, an external agent is putting energy into the system. Okay. And how do you get that energy out? Anybody? How do you think you can get that energy, that stored energy that you put into the capacitor? How do you think you can take it out? What do you think is happening to your, when you are using the flash of your camera? Your capacitor is getting discharged. There is a huge amount of surge of charges flowing and recombining. Positive charges and negative charges come together. All the excess negative charges will rush and go to the other plate. When it goes, what happens? Both of them will become neutral. or that stored potential energy becomes 0. So now answer this question. How do you pull out the energy that is stored? By allowing the positive and negative charges to recombine or come together. Are you getting this point, guys?
Yes, ma'am.
Yeah. So you store energy with separating out positive and negative charges. Positive and negative charges by themselves, the electric field doesn't allow them to do that. They like each other, they want to be together, that is stability. But then an external agent is artificially doing work and pulling them apart. So by doing that, it is putting energy. So there is an energy stored in the system. So what happens? How do you get this energy out? By allowing this positive and negative charges to come back together again. When they come back together again, the potential difference becomes 0, the potential becomes 0, and that energy is brought out in the form of light or any form. Okay, so this is how a capacitor stores energy. And so in charging a capacitor, you're depositing energy. By charging a capacitor, you are depositing an energy. And you're going to see that larger the charge, larger is the energy that you're going to store. Okay, and discharging means allowing them to recombine, the electrons and the positive charges to recombine. And in recombination, they lose their charges, they just become neutral, and the stored energy comes out of a system. Okay, so what I will do here is I'll just stop here. In the next class, I have to go fast. So kindly answer the class so that I can move fast. So in the next class, we are going to answer some questions as like, where is this energy stored? What is the expression for the energy and things like that? We'll see in the next class. Is that fine?
Yes, ma'am.
Yeah. Okay. So this entire chapter is only that much. What is the meaning of charging? What is the meaning of discharging? If you know, you understood the chapter. Okay then. Good day.